In this video, we're going to use the definition of differentiation that we've used in the past in order to create some rules for differentiating different functions in order to speed up the process. So the idea is that eventually we're going to create some different formulas in order to make our lives finding derivatives much simpler. So, in number one, we want to find the derivative of the function f, which equals c, and c is some constant number. Now, I'm still going to use the definition for derivatives, which still involves me doing the limit as h approaches 0 of f of x plus h minus f of x all over h. But if we do that, considering when we look at f of x, whether it's f of x or, and I'll say it down here, so f of x is just c, f of x plus h is just c, f of, you give me anything, f of 27, it's just going to be c. There's no x value to replace in the function, it's always equal to c. So our limit up top, the limit as h approaches 0 is, well, f of x plus h is c minus f of x is c all over h, and so our limit as h approaches 0 is 0 over h, or rather it's just 0. So our first differentiation formula, the derivative with respect to x of, there we go, of some constant c is 0. And let's think about what that means. If I draw a graph of this, and I'll do that over here, so there's just my coordinate plane. F of x equals c is some horizontal line that goes through c on the y-axis. So no matter what I plug in for x, the output is c, be it, say, 9 comma, or I guess that we'll call that 7 comma c, or over here, which is negative 4 comma c. Like, whatever we put in, the output is c, and so we have this horizontal line. And remember, the limit is evaluating the slope of that line at a given value. So the slope of this line, no matter what, is 0, and therefore the derivative of our original function is always going to be 0. Let's look at some more examples. In number 2, we're finding the derivative where f of x is equal to just x. So we'll again go through the definition where we use the limit as h approaches 0 of f of x plus h minus f of x all over h. And if we do this, well, f of x plus h, we replace our x with x plus h, so it just ends up being x plus h minus, and f of x is just x all over h. And I forgot, I just need to put that limit out front there. And so in the numerator, x plus h minus 8, or excuse me, minus x gives us h. We have h over h. I forgot again, but there it is. H divided by h is 1, so our result is 1. So in this case, f prime of x is equal to 1. Let's look at number 3. Here we're doing the derivative of x squared. So the limit as h approaches 0, and I'll just use this definition again here. So instead of x plus h, we take out x, put in x plus h. So x plus h squared minus x squared all over h. And so our limit as we approach 0 is x plus h squared gives us x squared plus 2xh plus h squared minus the x squared all over h. And then x squared minus x squared will cancel. And then we can cancel the h from each of these. And so our limit results in, well, if we put 0 in for h, we just get 2x. How about x cubed? I'll do the limit function again, or the limit operation again. So as we approach 0, x plus h being plugged in for x results in x plus h cubed minus x cubed all over h. And if I do x plus h cubed, that's going to result in x cubed plus 3x squared h plus 3xh squared plus h cubed, still minus x cubed all over h. And again, so x cubed minus x cubed cancels. Notice that we can divide the h out of all of these. And if I put the h, or the 0 in for h, doing direct substitution, well, this h becomes a nothing. 3 times x times 0 becomes a nothing. And so all we end up with is 3x squared. So the derivative of x cubed is 3x squared. And what I want to show you here is just kind of a coincidental thing, and I'll go to a new page to do so. When my function was x, the derivative was just 1. Or I can look at this as 1 times x to the 0. X to the 0 is 1. Anything to the 0 power is 1. Then times 1. When my f of x was equal to x squared, the derivative was 2x, or rather 2x to the first. X to the first is the same as just x. When my function was x cubed, the derivative was 3x squared. If we did x to the fourth, the derivative is going to be, I don't know we didn't do it, but the derivative is going to be 4x cubed, and hopefully you can follow that pattern. So what is the derivative if our original function is x to the n? Now what you notice here is that the original exponent of 1, 2, 3, or 4 became the coefficient. So down here in our derivative, the original exponent was n, and will be our coefficient. And it'll be multiplied by x to the, and our exponent became 1 less. The degree dropped by 1 compared to the original. And so how do we do 1 less than n? Well, we just say n minus 1. And so this is the general derivative that we can follow for power functions. And for now, we are done.